I would like to thank the organizing committee for giving me this opportunity to share with you a part of our work, study and comparison of nickel zinc oxide material on indium tin oxide, nickel and graphite substrates. For this presentation, I will start with a quick introduction, then I will move to the electrode deposition of nickel zinc oxide, the characterization of the films, their electrochemical performances, and I will finish by conclusion. Nickel zinc oxide is one of the most promising materials used in many applications as a sensor, catalyst for many reactions, water treatment, also for energy storage. These large applications is owing to its various properties rely on the elaboration method and the preparation conditions. Various methods have been approached to elaborate nickel zinc oxide, including chemicals such as hydrothermal, co-precipitation, physical deposition. These methods require high temperature and pressure conditions compared to electrochemical methods. This last is one of the most interesting material synthesis methods due to its low cost and large influence on the nickel zinc oxide properties. Using electrodeposition methods gives the ability to control many parameters: applied potential, applied current, scan rate, electrodeposition time, etc. So we can easily control the properties of these materials. So to electrodeposit the nickel zinc oxide, we used a 3-electrode cell, platinum as a counter electrode, saturated calomel electrode as a reference, and indium tin oxide, nickel, and graphite substrates as working electrodes connected to the potentiostat galvanostat. The composition of the first bath was the zinc nitrate and hexamine. The second bath was nickel sulfate. In this work, we are interested to study the nucleation and behavior of the materials and compare the performances of nickel zinc oxide material electrodeposited on different substrates. In our quest to determine the optimal potential for the electrodeposition of zinc oxide and nickel under these specific conditions, we employed a technique known as cyclic voltammetry. As you can observe in the obtained voltammogram, there are several distinct anodic peaks. This peak indicates that the potential range we can apply. To better understand the nucleation and growth mechanism of nickel zinc oxide on the indium tin oxide, nickel, and graphite substrates, the chronoamperometry method was employed by applying the potential of zinc oxide and nickel deposition. This latter was determined from the cyclic voltammograms as shown in the previous slide, corresponding to the anodic peak potential domain. The applied potentials on the chronoamperograms of the nickel zinc oxide materials were as follows: minus 1.21 volts for indium tin oxide, minus 1.21 volts for nickel, and minus 1.45 volts for graphite. The graph obtained through this method referred to as a current time transient or chronoamperogram. Its shape is typically characterized by 3 distinct parts. The initial part, part 1, corresponds to the formation of the initial nuclei, leading to a decrease in current. The second part, part 2, signifies the growth of these nuclei, resulting in increased currents. Beyond the peak maximum, the diffusion controlled region, part 3, contributes to a recorded current decrease until it reaches a nearly constant value. This method serves as a highly valuable technique for investigating the nucleation and growth processes within the studied system. As can be seen in all the applied potentials of the electrodeposition of zinc oxide and nickel on different electrodes, The current transients have almost the same form. Chronoamperometry shows that all the current transients exhibit a typical form for a diffusion limited nucleation process with three-dimensional growth of nuclei. Although there are two primary modes of 3D nucleation mechanism documented in the literature, which are instantaneous nucleation and progressive nucleation. For all the transients were presented in the last slides, the experimental recurrent density of the second part was plotted versus T to the power of 1/2 and T to the power of 3/2. As shown in this slide, the first plots display a good linear relationship for all applied potential with high correlation factors compared to the second plots. This implies that the electrochemical deposition of zinc oxide and nickel on the three different substrates exhibits probably instantaneous 3D nucleation. Before examining the electrochemical performance, we characterize the material obtained on different substrates through impedance measurements. The Nyquist plot from electrochemical impedance spectroscopy of the electrodeposited thin film shows that the material deposited on indium tin oxide, nickel, and graphites have respectively low, medium, and high charge transfer resistance. Similarly, for the constant phase elements, increase with the same order of electrodes, and for the factor N, decreases respectively from graphite, nickel to indium tin oxide. This result reflects that the nickel-zinc oxide material on indium tin oxide substrate has a good chemical activity than the others and a high specific area. The characterization using cyclic voltammetry of the electrodeposited material on the electrodes reveals that the surface decreases when changing the substrate at a scan rate of 50 mV per second. For the specific capacity, it is calculated using the following relation. According to the bar graph plot, it is evident that the material deposited on indium tin oxide has the highest specific capacity, while nickel exhibits an average capacity, and graphite has the lowest specific capacity. To sum up, all the current transients exhibit a three-dimensional growth of nuclei. The electrochemical deposition of zinc oxide and nickel on the substrates exhibits probably instantaneous 3D nucleation. Material deposited on indium tin oxide substrate has a good electrochemical activity and has high specific capacitance.